Okay, so today we're going to start talking about probability. The whole of Chapter 6 focuses on probability and the different types of it. Now, today we're going to start this introduction by talking about the three types of probability. Now, the first type of probability that we're going to talk about is called classical probability. Now, classical probability is also sometimes referred to as theoretical probability, and it's really based on prior knowledge. So classical probability, also known as theoretical probability, is based on prior knowledge. Now, a good example of that would be, you know that if you toss a coin, it's a 50-50 chance of getting heads or tails, 50% heads, 50% tails, if the coin is fair. Like, that's prior knowledge. That's something that you know. That's what we refer to as classical probability. Another good example of classical probability is rolling a die. There are 6 sides to a die, so you know you get a 1 out of 6 chance of rolling a 1 or a 2 or a 3. So that's based on prior knowledge. Yes?
So I've seen this thing go around where, like, if you try to roll a 6 on a die,
Yes.
you have a, like, 1 out of 6 chance.
Yes?
But I've also seen that you have a 50% chance. Like, either you roll a 6 or you don't.
Oh, that's like pass or fail. So yes, you're right that either you roll a 6 or you don't, but that doesn't mean it's a 50% chance, because either you roll a 6 or if you don't, that means you can roll a 1, 2, 3, 4, 5. So it's still a 1 out of 6 chance. That's a fair thought process, and we're actually going to talk about that later, so good question. Okay, the next one we're going to talk about is relative probability. We can also refer to relative probability as empirical probability, and that uses observed data to determine probability. So like an example of that would be like an insurance company or something like that. They're using observed data. They're using all of the data that they've collected off of their drivers to determine the probability that you will do something stupid. Now the final one is subjective probability. Subjective probability is based on experience and opinion. Okay, so when I talk about based on experience and opinion, that doesn't mean like it's not reliable. That just means it really has no data to back it up. So a good example of subjective probability would be that an owner of a business decides there's a 75% chance a new product will be successful. He's using his knowledge about the past and about his business to make an assumption. So, like, let's say the owner owns a scrub shop, right? They know if they buy the popular kind of scrubs, it's probably going to do well. They also know if they purchase a set of wrenches to sell at their store, it's not going to go well. That's an example of subjective probability. It's based on experience and opinion. Do we have any questions over these three types? What do we think about these explanations? Are they good explanations? Do they make sense to you? Good, good, good. Okay, now the next thing we're going to talk about is the probability line. This line represents all of the probabilities that you could have. Now, when we're finding the probability of something, okay, it's going to be written like this, probability of something, okay? Whatever you're going to find is going to be on the inside there for X. So the probability of flipping a heads on a coin or rolling a 6 on a die. Now, the probability of finding something is always going to be in between 0 and 1. So the probability of anything happening is going to be in between 0 and 1. Okay? That means it's going to be a decimal. Now, on this probability line, here's what that means. The lowest probability you could get is a 0, and the highest probability you could get is a 1. Okay? And that's inclusive. You can get a probability of 0, and you can get a probability of 1, 0 to 1 inclusively, okay? So what do you think this tick mark right here is going to represent? A half, okay? Now, sometimes probabilities will be written as a fraction like we have here. Sometimes probabilities will be written as a decimal, so like 0.0, 0.5, 1.0. Sometimes it will be a decimal, okay? Sometimes it will be a percentage, so 0%. What would this be as a percentage? 50%. This would be 100%, okay? So probabilities lie between 0 and 1 inclusively. Now, with that being said, here's what that means. If you get a probability of 0, if the probability of something happening is 0, that means it's going to be impossible. It is impossible for that to happen. The probability of that happening is not happening. It's 0, not happening, okay? If you get a probability of 1, that means it is certain, okay? It is definitely going to happen. The probability of me taking a nap today after school is 1. It is going to happen. It is certain. Are we on the same page? Okay. Then, the probability of 1/2 or 0.5 is as likely as not. Another way that you hear people talk about a probability of 50 is a 50-50 chance. There's a 50-50 chance that it's going to happen or it's not, okay? There is a probability of half or a probability of 50%. There's a 50-50 chance that I'm going to make supper tonight. Either I am or I'm not. I don't know. Haven't decided yet, okay? Now, if you get any probabilities in this area here, in between 0 and 1/2, so like a probability of 0.25, 0.3, a probability of 0.179, okay? These probabilities are unlikely. Doesn't mean it's not going to happen, but it's not likely that it's going to happen, okay? Now the probabilities is between 1/2 and 1, so like 0.75, 0.8, whatever, those are likely. We're not saying it's a guarantee, but they're pretty likely that it's going to happen. Wow, I'm going to have that kind of day today. Whew. Maybe the probability that I'm not going to cook supper is going up a little bit. Maybe it's more likely that I'm not going to make supper tonight. It might be a Cancun kind of night. Last night was National Pizza Day, and I wasn't aware of that, so maybe I have to get pizza to celebrate a day late. Oh, no. Oh, no. Oh, shucks. Okay, here we go. What? Yes, sir. The next thing we're going to talk about is vocab. Vocab's pretty important. Vocab's something that's going to be on the test. So, the first thing we're going to talk, an experiment, guys. An experiment, E-X-P-E-R-I-M-E-N-T. An experiment is a repeatable procedure with a set of possible results. Right? So like an experiment in science, an experiment wherever, an experiment is a repeatable procedure with a set of possible results. A really good example of an experiment is throwing dice. Now while you guys are writing this down, I'm going to get some vocab. I'm going to talk some English language here for a second. We talk about dice a lot in statistics. When you have multiple, when there are multiple, it is dice. When you only have one, it is a die. Okay? So you do not have one dice, you have a die, but then if you have two or more, it is dice. Okay? Dice or a die. I know that sounds weird because you're like, nah, but that's what it's called. Okay? The next thing we're going to talk about, a sample space. I don't know why there's an in there. A sample space is a possible result of an experiment. A sample space is a possible result of an experiment. So if we're talking about the experiment of throwing a die, not dice, if we're talking about an experiment of throwing a die, the sample space would be all my possible results. So I could get a 1, I could get a 2, I could get a 3, a 4, a 5, or a 6. That is the sample space of throwing a die. Now, the sample space of throwing multiple dice is going to be different. But if you're rolling a single die, That's your sample space. Those are your possible results. Okay? Now this one, man, my grammar is terrible when I make this. Should have an N. An outcome is all the possible outcomes of an experiment. All the possible outcomes of an experiment. So, an example would be rolling a 6. That would be an outcome of rolling a die. Right, Keaton? Okay. And then finally, an event is one or more outcomes of an experiment. One or more outcomes of an experiment. So, if I were looking at this example that we've been looking at this whole time, rolling an even number is an event. It is an outcome of an experiment. It is event. Okay? Another one that could be like with a different experiment, you could say that getting a tail when tossing a coin, that could be an event. All right? Those are our new vocab talking about probability. Now, the next thing we're going to talk about is Dr. John Carriage. Okay? You don't have this on your practice. This is just going to set us up for what's coming later. Okay? Dr. John Carriage was born in 1903 and he died in 1985, and he is famous for the relative frequency approach. He was a South African mathematician, and during World War II, he decided to go up and visit his family in Denmark, and while he was there, the Nazis invaded, and he was captured and placed into a prisoner's camp. Now, he did survive, obviously, but there was a lot of time to pass in that prisoner's camp. So him and another one of the prisoners that he felt comfortable with, they decided to toss a coin 10,000 times to pass the time. Now, we're assuming that this coin was fair. You also have to think this was during the Holocaust, right? So maybe the coin was nicked a little bit here or there, but for the most part, this coin was fair. And after tossing that coin 10,000 times, he achieved 5,067 heads. So he would flip the coin and his partner would document. That way it stayed consistent. So he tossed it 10,000 times and he got 5,067 heads. Now, in Carriage's experiment, if we assume that the coin was fair, what was the expected number of heads? How many heads would you have expected to get? 5,000, right? Because you flipped a coin 10,000 times, and we know, based on prior knowledge or classical probability, that it would be a 50-50 chance, okay? Now, what was the difference between the observed and predicted number of heads? Yeah, we would take that 5,067, and we would subtract the 5,000 that we expected to get, and there was a difference of 67 heads. Now, what was the relative frequency of the heads in this experiment? Remember, relative frequency is you're going to take what you achieved, and you are going to divide that by how many you actually did. So that would be 5,067, and we're going to divide that by 10,000. So what was the relative frequency of that? Say that again? 0.5067. Okay? So the relative frequency of heads in this experiment was 0.5067. Now part D says what is the difference between the relative frequency and the probability? So we said that 0.5067 was my relative frequency, and what was the probability, do we think? 0.5 or 50. What's the difference between that? 0.0067. Now, when you think of it in the grand scheme of things, because you're looking at it and you're like, 5,067 heads, what the heck? He should have gotten 5,000. Well, in the grand scheme of things, guys, 0.0067 is not that far off. He kept going, and he really got pretty close to what we should have gotten, which really just kind of proves that it is a 50-50 chance. Now, the next thing we're going to talk about is the law of large numbers. Again, this is not on your practice. I'm just giving you some information here. The law of large numbers states, as the number of repetitions of an experiment increases, the relative frequency of an event tends to approach the actual probability, which you'll notice with Carriage's experiment. He flipped the coin 10,000 times, And I'm sure, like, when he first started, maybe he got 5 heads in a row, and he was probably a little bit nervous, like, maybe this isn't 50-50. But the more times he did it, the closer he got to that 50-50, and that's where the law of large numbers comes into play. Now, a lot of people get the law of large numbers confused with the law of averages. So the law of averages, here's a good example. When a batter comes up to the plate, I can't type either, late in the game, without a hit, sportscasters, you'll hear them say, he's due for a hit, right? Or a gambler who has had a run of bad luck will say, my luck is due to change. The difference between the law of averages and the law of large numbers is this. Both of these statements are based on a principle often referred to as the law of averages, but the law of averages is not valid. There is nothing to support it. The gambler who says he's had a run of bad luck might be correct that his luck has been bad, but he is no more likely to have a run of good luck now than he was when he began. The baseball player who has not gotten a hit is no more likely to get a hit now than before his slump. That stuff is not based on probability. That stuff is based on like skill or talent. Does that make sense? So the law of averages is not valid. That's how they get you in Vegas. They think that you're over here and you're like, well, I've been playing and playing and playing and playing, and I've been doing so bad, I'm bound to do better on the next one, and you go again, and you're going to lose because the law of averages isn't a thing. It's not valid. Are we all on the same page with that? But the law of large numbers is, as the number of repetitions of an experiment increases, the relative frequency of an event tends to approach the actual probability. And the actual probability in Vegas of you winning is very small. Don't gamble. It ain't worth it. All right. Now, on your practice, the next thing we're going to talk about is statistical inference. Statistical inference involves the use of sample data to form generalizations or inferences about a population. Okay? So, the probability of an event happening. To find the probability of an event happening, you have to take the number of ways that it can happen and divide that by the total number of outcomes. So let's look at this first example. What is the probability of rolling a 3 on a fair die? What are the total number of outcomes that you could have on a fair die? There are 6. You could get a 1, 2, 3, 4, 5, or 6. Now, we want to figure out the number of ways that it can happen. The probability of rolling a 3. How many different ways can you roll a 3? Just one. So the probability of rolling a 3 on a fair die, and that's how we write it, P followed by the parentheses, that stands for the probability of rolling a 3 on a fair die, is the number of ways it can happen divided by the total number of outcomes. So that would be 1 over 6. Now, if we put that into our calculator, 1 over 6, what are we going to get? I'm going to say about 0.16 repeating, 0.167, 0.17, something along there. Now, if you compare that to our probability line up top, do you think this is impossible, unlikely, 50-50, likely, or certain? This is unlikely. Doesn't mean it won't happen, because you guys know as much as I do that I have rolled a 3 on a die, and so have you, but the chances are low. So, on number 7, or the next example, there are 7 marbles in a bag. 5 are red, 2 are blue. You reach your hand into the bag and grab 1 marble. What is the probability that you choose a blue marble? So, we need to start with the total number of outcomes. How many blue marbles do we have? 2. Then, the total number of ways it could happen. What are the total number of things that you could pull out? There are 7 marbles in a bag. So the probability of getting a blue marble would be 2 out of 7. So in our calculator, 2 out of 7 is going to be about 0.29. Okay? So what do we think? Impossible, unlikely, 50-50, likely, or certain? Unlikely. Yes? Oh my gosh, yeah, I got those switched. My bad. Yeah. There are 7 total outcomes, and there are 2 blue marbles. Thank you. I was in my head. No, we did the probability right. I just wrote down the thing wrong. Now, my next question to you, which is more likely to happen? You rolling a 3 on a fair die, or you pulling a blue marble out of this bag? Blue marble. Now, it's not a ton more likely, but it is more likely than rolling a 3 on a fair die. Okay, a spinner is made of 5 congruent sectors. The spinner is spun once. What is the probability that the spinner will land on an odd number sector? So when they say a spinner is made of 5 congruent sectors, it's like you have a pie chart and they split it into 5 sections, and each of them are like the same width, and so you're going to spin this spinner, and it says what's the probability that the spinner will land on an odd numbered sector? So we're going to have sector 1, 2, 3, 4, and 5. So what are the total number of outcomes for this spinner? 5. We can land in one of these 5 sections. The number of ways that we want it to happen. We want it to land in an odd numbered sector. So how many odd numbered sectors do we have? 3. So the probability that a spinner lands on an odd numbered sector is 3 out of 5, which we know is 0.6. So what do we think? Is it impossible? What is it? It's likely. Very good. It is likely. Okay. Next one. A card is chosen at random from a shuffled standard deck of 52 playing cards. What is the probability that a face card is chosen? So let's start first here. Let's talk about a standard deck of shuffled cards. Okay, we are going to refer to a deck of cards a lot this semester, so let's just kind of get the fair understanding. How many suits are there in a deck of cards? 4. There's hearts, clubs, spades, and diamonds. How many colors are there? 2, red and black. Okay, how many cards are there in each suit? 13. We go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen. Okay? So, the total number of outcomes. How many total possibilities do you have when drawing a card? 52. Now we need to talk about the number of ways that it can happen. We want to draw a face card. Now, face cards are the jacks, the kings, and the queens. How many jacks are there in a deck? How many kings are there? How many queens are there? Okay, so how many total face cards are there? So we want to draw a face card. There are 12 ways that that could happen. Now, the probability of drawing a face card is what you want over the total, so 12 over 52. Can that simplify? Absolutely it can. 4 goes into both of them, so that's going to be 3 over 13, which is approximately what? 0.23. So what do we think? It's unlikely. Could it happen? Yeah, it happens all the time, but it's unlikely. All right. Show me your thumbs. How are we feeling on this basic concept? Good. Good. Just kind of a refresher. You guys have done some of this in the past. The next one is a little different. A fair coin is tossed 3 times. What is the probability of obtaining 2 heads and 1 tail? For this problem, let's write out the sample space to determine the total number of outcomes. Now, if you forgot what the sample space was, you can go back to the front page. And a sample space is a possible result of an experiment. So the sample space of throwing a die was 1, 2, 3, 4, 5, 6. So we want the sample space of tossing a fair coin 3 times. Now, there's a couple of different ways you can do this. All right, the first one is you can literally sit there and you can think through. I could toss 3 heads in a row. I could toss a head, then a tail. I could toss a head, then a tail, then a head. I could toss a tail, then a head, then a head. I could toss a tail, and a head. I could toss a tail, a head, and a tail. I could toss, 1, 2, 3, 4, 5, 6. Where am I at? Head, tail, tail. Very good. Head, tail, tail. And then I could toss all 3 tails, right? That's one of the ways. But did you notice that right there I was like, takes a little bit of thinking, right? Another way that you could make this sample space is what's called like a tree, okay? So you could say, all right, the first time I toss a coin, what are my options? A head or a tail, right? Now, if I toss a head and then I go to toss it the second time, what are my options? A head or a tail, right? If I toss the tail the first time, what are my options for the second toss? Still a heads or a tails, right? Then when I go to toss the third coin the third time, no matter what I get on the first 2 times, what are my options? Heads or tails, heads or tails, heads or tails, heads or tails. And what that does is that gives me all of my possible options. Check this out. Here's my first option, heads, heads, heads. Here's my second option, heads, heads, tails. Here's my third option, heads, tails, heads. I highlighted the wrong thing. Heads, tails, heads. Here's my fourth option, heads, tails, tails. Do you guys see what I'm saying? So to write this sample space, whatever way makes the most sense to you is okay. Here's how we write our final answer. We have the the set brackets, and we list them out. So my first option was heads, heads, heads. My second option was heads, heads, tail. Or I could have done heads, tails, heads. Or heads, tails, tails. Then that handles all of the options on if I tossed a head first. My second set here is if I toss the tails first. So I have this option. That's a pen, not a highlighter, I guess. What are you doing? Tails, heads, heads. We could have tails, heads, tails. We could have tails, tails, heads. We could have tails, tails, tails. So, tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. So can you tell me how many possibilities of outcomes could you get? What is the size of my sample space? 8. There are 8 possibilities for when you toss a fair coin 3 times. Now, that would be under my total outcomes, my total number of outcomes. But next, we want to know the number of ways it can happen. So they wanted to know what is the probability of obtaining 2 heads and 1 tail. So if I come here, that's 3 heads, that doesn't work. 2 heads and 1 tail, that's 2 heads and 1 tail. It doesn't say what order. That's 1 heads and 2 tails, that doesn't work. 2 heads and 1 tail, 2 tails, 1 head, 2 tails, 1 head, 3 tails. So how many different ways can that happen? 3. Now the probability of getting 2 heads and 1 tail is 3 over 8. All right, what is that as a decimal? 0.375? So what do we think? Likely, unlikely, certain? Unlikely? Any question? Okay. Now, that leads me to our next topic here, selection with replacement. The formula for knowing how many items are in the sample space. So tossing a coin is one example of selection with replacement because the coin does not remember what was tossed each time. If you toss a heads the first time, that's not going to impact your second toss. That's not going to have any effect on it. There are always the same number of outcomes each time you toss the coin. Other examples of selection with replacement would be multiple choice tests or true or false tests. Because when you choose an answer, it doesn't like take it away from the answer or from the possibilities, okay? This is the formula that we are going to use to figure out how many possibilities are in our sample space. Because when it said toss a coin 3 times, we could find out what that sample space was, and we found out there were 8 possibilities. But what if I asked you to toss a coin 4 times, or to toss a coin 10 times, or to toss a coin 100 times? Coming up with all of those possibilities would be unrealistic, and it would take forever. So this formula right here is going to help me figure out how many possibilities are in our sample space. So first thing we're going to look at is this letter N. N represents the number of choices. N represents the number of choices. And K represents the number of times the experiment was repeated. Okay, so the number of choices raised to the power of the number of times the experiment is going to be repeated. So using this information, answer the following questions. What would be the total number of outcomes if we tossed a coin? If we tossed a coin, how many choices do we have? 2. We have heads or tails. Now, if we're going to toss it 3 times, what variable would that go in for? 3. So if we tossed a coin, which has 2 outcomes, 3 times, we're going to have 8 possible outcomes. The size of our sample space would be 8. Now, if we tossed a coin 4 times, how many choices do I have still? I still have 2. That's not going to change. But how many times am I repeating the experiment? 4. What is 2 to the 4th? 16. The size of the sample space would be 16, which is still not impossible to come up with by hand, but it's not ideal. Okay, what about 5 times? 2 to the 5th, which is 32. What about 10 times? 2 to the 10th, which is 1,024. 1,024 possibilities in our sample space. There is no way. You could not pay me, well, I bet you could pay me some money, but you could not pay me a low amount of money to come up with all of those possibilities. Listen, I have my price. If you want it, you can come talk to me later. All right. Now, the next question says, what is the probability of getting all tails when tossing a coin 10 times? Now, when you have a problem like this, I want you to think very carefully about what they're asking, okay? Now, the probability is the number of ways that it can happen out of the total number of outcomes. We already know that the total number of outcomes is what? 1,024. But I want to know, how many ways can I flip a coin all tails? Just 1. I want you to think back to this sample space right here. Even when there were 3, even when I only tossed a coin 3 times, how many ways could I only toss a tails every single time? Just 1. That's not going to change. So the probability of getting all tails when tossing a coin 10 times is going to be 1 out of 1,024. Now, I don't really care about the decimal on this one. You don't even need to know the decimal to tell me, is this likely or unlikely? Unlikely. It's almost impossible. It's going to be pretty close to 0. It's almost impossible. Now, a test has 5 multiple choice questions with 4 choices each. In how many ways can a student answer the question? So, to figure that out, we want the number of ways that it can happen. Oh, nope, sorry. We want to use this guy right here. I was looking at the wrong one. And how many ways can a student answer the questions? So, how many choices do they have for their multiple choice test? 4. There are 4 choices for each. And how many times are they going to repeat this experiment? 5, because there's 5 questions. So you are going to have 4 choices raised to the power of 5 questions. And what do we get? 1,024. There are 1,024 different ways that a student could answer these questions. Okay? Now, part B says, if a student is purely guessing on each question, what is the probability that a student will guess all 5 correctly? 1 out of 1,024. There is only one combination of all of these answers that are going to get them correct. So they have a 1 in 1,024 chance. But I need you to understand, when I give you a test and it's multiple choice, that doesn't mean your probabilities of doing well are this low. Because you have studied for that test, you know the information, that changes your probability. This would be like if I took a calculus multiple choice exam and I gave it to a kindergartner and I said, circle the right answers. What are the chances? What's the probability that they're going to get them all right? Well, they're guessing, so 1 in 1,024. Okay? All right. List the sample space for each or for the following situation. Tyler went to an ice cream shop and he was offered the following options. He could choose one of each of the following categories: chocolate or vanilla ice cream, with fudge or whipped cream, and sprinkles or brownies on top. So we want the sample space. He can only choose one of each category. So here's my first category, which is ice cream. Second category, which is fudge or whipped cream. And third category, which is sprinkles or brownies. So the first thing I'm going to do is I am going to give these a variable. So what would be a good variable for chocolate? C. What about vanilla? What about fudge? What about whipped cream? What about sprinkles? And what about brownies? Okay, so I want to come up with the sample space of all of these possibilities. So I'm going to start with my set bracket here. And you can do this however you want. You can work through it in your brain, or you can make a tree. I don't care. Figure it out with your table partner. Those of you in video land, pause the video and come up with a set sample space on your own. Okay, so it doesn't matter what method you chose to come up with your sample space. I chose to make a tree because it makes sense to me. I said my first choice could have been chocolate or vanilla. If I choose chocolate, then I can choose fudge or whipped cream. And regardless of fudge or whipped cream, I can choose sprinkles or brownies for each. Then the same thing for vanilla. So that gives me my first option here, chocolate, fudge, and sprinkles. My second option, chocolate, fudge, and brownies. My third option, chocolate with cream and sprinkles. My fourth option, chocolate with cream and brownies, and so on and so forth. Now, if you were to take a wild guess, what is the probability that you would guess Tyler's exact choices correctly? 1 out of 8. Now, Tyler, what would you choose?
I would probably choose vanilla, fudge, and brownies.
Vanilla, fudge, and brownies? Do we agree? That's probably what I would have chosen, honestly. Good choice. Good choice. All right, next page. The next thing we're going to talk about is a dice chart. This is a very common sample space. Guys, this is a very common sample space that's used in probability. We're going to use it a ton. And it is the set of outcomes from rolling 2 dice. If there are 6 different outcomes for each die, and you will roll 2 dice, how many outcomes will be in the sample space? Let's answer this question first. If there are 6 different outcomes for each die, and you are rolling 2 dice, how many outcomes will be in the sample space? So, the 6 outcomes happening twice tells me how many outcomes am I going to have? 36. That's the size of my sample space. Now what we're going to do is we are going to create the sample space, okay? Now, the first die that I'm going to roll, how many options do I have? 6, right? I'm going to be able to roll a 1, 2, 3, 4, 5, or 6. What about the second die? How many possibilities could that give me? 6. 1, 2, 3, 4, 5, or 6. Now the sample space for this is going to look a little different. The sample space is going to say, okay, if I roll the first die and I roll a 1, then I roll the second die and I get a 1, right? What would the sum of those 2 dice be? 2, right? Now, what if I rolled the first die and I got a 2, and I rolled the second die and I got a 1? So, what would that guy be? What would that sum be? 3. So, this sample space is going to be the sum of your column and row. So, this is going to be 1 plus 3, which is 4, 1 plus 4, which is 1 plus 5, which is, and 1 plus 6, which is. Do you understand? So this guy right here would be the sum of 2 and 1. I could roll a 2 and a 1 and have a sum of 3. I could roll a 2 and a 2 and have a sum of 4. Go ahead, take a second, and finish filling out that table. So what is the highest sum that you could get when rolling a pair of die? 12. Because you could roll a 6 and a 6. That's the highest you could get. What is the lowest sum that you could get? 2. What is the most common sum that you will get? How many sums of 6 do we have? 5. How many sums of 7 do we have? 6. So what is the most common? Okay, so this is a really common sample space that we are going to use quite frequently. There are 36 options that you can choose from. Now the next thing we're going to talk about, it says, now use the sample space to answer the following questions. What is the probability of rolling a sum of 11 when 2 fair dice are tossed? So here's how we're going to write that. The probability of rolling a sum of 11. That's how you write that. Probability of rolling a sum of 11 when 2 fair dice are tossed. So if you look up at your sample space here, how many sums of 11 do we have? We have 2. So what are our possibilities, which are 2, out of the total outcomes, which are 36, which is 1 out of 18. Okay? What do we think? Likely or unlikely? Unlikely. Very good. Now the next one says, what is the probability of rolling a sum that is a prime number when 2 fair dice are tossed? So rolling a sum that is prime. So let's look at the prime options here. I'm going to highlight them in blue. Is 2 a prime number? Okay. Is 3 a prime number? And how many 3s are there? 2. Is 4 a prime number? Is 5 a prime number? Okay. Is 6 a prime number? Is 7 a prime number? Is 8 a prime number? Is 9 a prime number? No, because what can go into it? 3. Okay, is 10 a prime number? Is 11 a prime number? Yes. Is 12 a prime number? Okay, so how many prime numbers do we get here? 1, 2, 3, 5, 6, 7, 15. So that's going to be 15 out of 36, which is 5 out of 12. What would that be as a decimal? Can you guys tell me? 0.41 repeating 6. Okay, whatever. Likely or unlikely? Unlikely, but is it more or less likely than the probability of rolling a sum of 11? It's more likely than rolling a sum of 11. That's something you might actually see. Okay, a probability of 0.41 isn't terrible. It's just unlikely. Last thing we're going to talk about is a two-way frequency table, also known as a contingency table. Okay, so here I have a table for you, and it says the number of times students visited tutoring. Okay, now we are comparing full-time students to part-time students, and there are 3 different categories here. They visited tutoring 1 or fewer times, between 2 to 3 times, and 4 or more times. Now, if you'll notice over here, there's total columns. Let's go ahead and take a second and find the totals. If you were on Excel, this would be a lot easier because you would just type in equals sum and highlight these three cells, but we're doing it by hand, so we need to take 12 plus 33 plus 14, and that is 59, and 4 plus 7 plus 6, which is 17. We also need to take 12 plus 4, which is 33 plus 7, which is, and 14 plus 6, which is, then this little cell right here, you are going to double check that you did your math right. You're going to find the total of this category, and you're going to find the total of this category, and they should be the same. So what's 59 plus 17? And then what is 16 plus 40 plus 20? Okay, so how many total students did we survey here? We surveyed 76 total students. So on number 3, it says, find the probability that a student is full-time and visited one or fewer times. So I'm going to look up here at my two-way frequency table, and we want the probability that a student is full-time, so that's this guy right here, and that they visited one or fewer times. So you're looking for the intersection of those two highlights. So how many full-time students visited one or fewer times? 12. So the probability that a student is full-time and visited one or fewer times is 12 over what? 76. Now that can be simplified. I don't care if you simplify it or not. Let's just put it as a decimal. 0.16, about 1.16. Okay. Number 4, find the probability that a student is part-time, so that's this guy right here, and visited 4 or more times. So what is the intersection of part-time and 4 or more? 6. Out of how many total? 76, which is approximately 0.08. Now number 5 just wants the probability that a student visited 2 or 3 times. Did they specify whether it had to be full-time or part-time? No. So they only care about 2 or 3 times. Now, a student that visited 2 or 3 times, how many total did we have there? So that's going to be 40 over our total number of students, which is 76, and that's about 0.53.